the last particle we need to look at for the standard model is the Higgs boson. Now, we're not really going to go into this in much detail other than to sort of talk about why it's needed, where it was first discovered, and the reason why it is important is that the standard model had a bit of a problem to begin with. It initially predicted that some of the particles, and in particular the leptons, quarks, and also the some of the bosons, so the W and Z bosons, it predicted that those particles should have zero mass. And we've seen already that that's definitely not the case, that these particles do have masses, and in fact the leptons increase in mass, likewise the quarks, as we go across the generations, and that it's not what has been observed. So when we when experiments were done measuring these particles, we definitely saw that these particles had mass, and so this idea of the standard model predicting that they should have zero mass was a bit of a problem. In order to sort of deal with that particular situation, a scientist by the name of Higgs, along with a few other people, came up with a mechanism. So this mechanism, we're not going to go into it in too much detail, but came up with this mechanism where particles gain mass, or sort of are given mass in a sense, when passing through the Higgs field. So in the same way that we have gravitational fields, electric fields, magnetic fields, we had this Higgs field was proposed as being the thing that allowed particles to have mass, and that particular mechanism was introduced to solve this problem of some of these particles not having zero mass. And the helpful thing about that is that it wasn't just this mechanism that sort of explained something. A point to note here as well is that the more strongly a particle interacts with the Higgs field, the greater its mass. So we can see then that if we go back and have a think about some of the leptons and quarks, for example, those particles that have greater mass are the ones that interact with the Higgs field more significantly. So have this mechanism that explains what's going on with mass, and gives us a bit of an explanation behind why some of these particles have mass. The other useful thing about this particular mechanism is that it predicted the existence of another particle, and as I'm sure you can guess, that particle being the Higgs boson. So this theory could be tested experimentally because it predicted that Higgs boson. So the Higgs boson itself is probably not the most significant thing of this mechanism. It's simply just that we see that there is this particle that goes along with the Higgs field, and by being able to test for it experimentally, we could then confirm whether or not this particular idea of the Higgs field and the Higgs mechanism, it allows us to confirm whether or not that does actually make sense. So the Higgs boson was the particle that was important in this particular line of discovery. And finally, so this is sort of a number, 40, 50 years past when the Higgs boson was first proposed, so 2012, 2013, the Higgs boson was confirmed. So experiments were conducted at CERN that showed a particle that had all of the properties that matched up to those predicted by theory that the Higgs boson should have. So by instituting this this fix, I suppose, to the standard model, we were able to then identify that there was this particle that confirmed that particular theory. Now, the Higgs boson itself, so it is another boson, but it's a bit different to the other bosons that we saw, the gauge bosons. So it basically is now, it mediates something, but not so much a force. It mediates the particle interactions with the Higgs field. So whereas the other bosons mediate forces, fundamental forces, the Higgs boson is mediating the interactions with the Higgs field itself, and so it's not actually mediating a force. So if we think about some of these points that I've just made there, things like leptons and quarks, W and Z bosons, they obviously then do interact with Higgs field. Particles or bosons, I suppose, such as photons, they're massless, so that means that they don't interact with the Higgs field. So any particles that are massless obviously can't be interacting with the Higgs field. One last point here too is that the Higgs boson itself doesn't actually give all particles mass. So baryon masses, for example, so when we combine three quarks together, the mass of a baryon is mostly actually due to the binding energy of the quarks themselves. So it's less than about 1% is the amount of mass that's contributed by the Higgs boson in that sort of scenario. So when we say that the Higgs boson gives particles mass, it's only some. It doesn't actually contribute to things like baryon masses that significantly, which is actually more due to binding energy of the quarks.